Ignacio did the PhD at the University of Cantabria, the north of Spain, under the supervision of Enrique Martínez González and Joe Silk. And after that, he moved with a postdoc to the University of Oxford, and after that to the University of Zurich. And then he got a permanent position at the University College London, where he's presently working and where he's a reader. Today he's going to talk about the evolution of massive early-type galaxies, both from an observational point of view in stellar population and also in dark matter. He will be here until the end of the week, so if anyone is interested in talking with him, he's presently at the room where is Ignacio Garcia La Rosa, and if you also can contact with him through me. Okay, thank you, Ignacio.
Thanks, Nacho. It has been a real pleasure, and thanks for the invitation to come here to the AAC. I have been visiting already for 5 weeks, which has been really nice, especially getting away from the horrible weather we have been suffering back in the UK with lots of rain. And as Nacho was saying, I'm going to be around until, so including tomorrow, Friday. So if you have any questions outside of this, by all means, drop by my office. Okay, so what I'm going to talk about here is a bit of a medley, a potpourri of different aspects of the issue of galaxy formation. And I wanted to have this dichotomy, this Star Wars type of argument, the dark side and the bright side of galaxy formation, and especially concentrated on massive early-type galaxies. And I will try to convince you of the reason for choosing especially massive early-type galaxies. So I'm actually going to skip. I'm going to go for this one instead. So in the different steps that we have in the process towards galaxy formation, we begin with small fluctuations. So we are actually starting already 300,000–400,000 years after the Big Bang, as you know. So we have the small density fluctuations, as you can see there in the cosmic microwave background, there in the arrow. Those small fluctuations have also a higher than actually fluctuation in the dark matter content, which is another component in the system that you can see here. And those fluctuations grow. On the one hand, we have the dark matter here, as you can see in the simulation, but we also have baryons, ordinary matter, that can lose energy and they fall inside the potential wells created by the dark matter halos and start forming stars, the luminous component that we see. So you see that there is a long way, a long road from the small fluctuations all the way to the galaxies or even the stars we see in our neighborhood. And the big problem is mainly in pretty much this step over here. So as usually one says, this region here is dominated by linear physics. So in principle, even though it's complex, you can basically treat the system in a reasonably okay way. So there are not enormous, if you want, uncertainties within the paradigm that we have, of course. The evolution of the fluctuations in dark matter is pretty much driven by gravity in an expanding universe. So it's not that bad to understand. The process of galaxy collisions, mergers, and formation gets really complicated because you begin to deal with the physics of gas. So, for example, the way gas is losing energy and falling into the central parts of the galaxies, the way this gas is fragmenting into molecular clouds and forming stars. And this is a horribly complicated process. This is basically the bottleneck of our understanding of galaxy formation. So that's why this is very important to try to connect both, because on the one hand, the real thing that we can observe through telescopes most of the time is this, stars, galaxies, and the driver of a big part of the evolution of structure in the universe happens to be the dark matter, which we don't see. So it's important to know that. So just going back to the other slide, the central tenet of all this paradigm that we have is the concept of a two-component system, where you have the dark matter, which is collisionless, only interacts through gravity, and then the baryons, which is the gas, which is collisional, it's dissipative, you can lose energy, and you form stars, which would be similar to dark matter particles in a way. So you have a complex situation between the two. And you see that the process can be, well, oversimplified to having an initial system with a small density fluctuation where you have both dark matter and baryons like so. And then you just evolve into a system like this, where you have most of the baryons actually living in the central region, dominated by stars, and the dark matter in the outer region. So that's more or less the structure. The reason why massive galaxies are important and very interesting for these studies, even though they represent a small amount of, in terms of numbers of galaxies, they're actually a small community, if you want, compared with the bulk. However, they're very interesting because they have some sort of dichotomy between the two ways of looking at them. So on the dark side of it, if you want the dark matter part of it, we have the inherent hierarchical build-up of the structure. So that means that if you have a massive galaxy, that structure has to form through successive mergers, where you basically keep on adding more stuff to your system. So that means massive galaxies should have a very complex history. You see here a low mass structure, a high mass structure, and you see the high mass structure has a richer, more complex history of mergers. This is basically the way the different dark matter halos merge. Whereas on the other side, when you look at the baryons, mainly you look at the stars, you actually see they are dominated by old populations. So all these galaxies, all these massive galaxies feature very old populations, which means that no matter what, no matter how complicated the thing can be there, all these stars were formed very early on. So it's not as simple maybe as I'm putting it now, but the big picture is that basically most of the stars were formed very early on, very, very quickly. So there's some sort of dichotomy between the two that we need to understand. This has been interpreted in various ways, and one of those that I think is actually very interesting and very useful to work with is this one, the so-called the color magnitude, in this case color mass diagram, where you see each point here in this cloud represents a galaxy, and you see that when you put them, they don't live in this diagram at random. They dominate two main regions. You have the cloud here called the so-called blue cloud, because you have blue colors dominated by low mass galaxies, and you have the red sequence, which is dominated by the more massive ones. You see here at the massive end, pretty much all your galaxies happen to be belonging to the red sequence. So you have a very interesting connection between the two. There's even a green valley that people came up with. This is a very highly pictorial view. But the interesting bit is that you can try to interpret this, which is an observational graph, with respect to more theoretical cartoon approaches, if you want. This is from the paper of Sandy Faber in 2007. And you can see that the way of populating all this diagram is that you can basically, again, we are thinking of a hierarchical structure. So that's quite important. So you have to start from down here, low mass. And because down here you have mainly blue cloud galaxies, basically you have star-forming objects that at some point end up being promoted to the red sequence. So either they are promoted like this, you have very quickly quenching there, and then they go up, you basically climb up the red sequence via gas-poor mergers. The reason for being gas-poor is that if there is some star formation here, it will become blue, and it will go down here again. So you really need to have all this process happening without any star formation. If you want to have more star formation in between, what you can do is that the quenching happens in different stages with respect to mass. So this region, and this region of the red sequence get populated from different regions of the blue cloud. So that's another option. And yet another option, which would be maybe the more realistic one, is a combination of the two. You have different points of quenching of star formation, and then you have possibly dry mergers climbing up. But the thing is, the real thing is actually going to be more complicated, as I will show you, especially with massive galaxies, because now what you try to explain is what type of track explains the objects that you see up there, or if you want, here in the observations. And that's the important bit. Sure. Yeah. Yep. Exactly. Yeah. Good. Yeah. Yep. True. Absolutely. Absolutely. So that's why, as I said, I'm showing here some sort of simplistic argument. Here, this is everything at redshift 0. But of course, when you're dealing with these things, you're actually in your model, you're taking care of those things. So for instance, when you observe galaxies at high redshift, you still find that most of your massive galaxies are still populating the red sequence. You have a fraction of them in the blue cloud. So you're right. Basically, you begin to have more star formation in more massive galaxies, which means that you're seeing the buildup of this. So this is, if you want, a snapshot at redshift 0. But what I'm saying is that as time goes on, interestingly enough, some of these regions are actually more stable than they would basically appear otherwise. If you think, for example, there is very strong evolution, you may think that this sequence actually, if you go to redshift 1, this sequence is no longer there. And that's not true. You have a very significant number of massive galaxies at redshift 1. So those objects are still there. But anyway, yeah, that's a fair point. Another interesting diagram is this one, which connects again the dark component and the bright component of galaxies. And here it's basically I'm not going to go into details, but the bottom line is you have dark matter simulations and you have real observations of galaxies, and you try to put them together. And what you say is that for this halo, I end up getting you do a sort of a one-to-one mapping between the halo that you see, the galaxy that you see and the halo that you think that galaxy could be having. And then you have a so-called baryon fraction. So what is a fraction of stellar mass with respect to the total mass, which is this little m stellar mass, capital M, the total mass. And what you see is that when you plot them according to the whole mass of the system, here in this case the mass of the halo, you find that this baryon fraction actually reaches a peak at galaxies that have stellar masses of order a few 10 to the 10 solar masses. And then the baryon fraction drops in towards both directions, going towards a dwarf regime and going towards a giant regime. That's actually a very interesting thing, because this is telling you that at least you must have two mechanisms, or a very crazy one. But normally, if you have two simple mechanisms, they must be present at the same time and operating in opposite directions. So that basically one controls, if you want, the dwarf regime, the other one controls the giant regime. And that's indeed what we think in this, if you want, these lines that I put here, that we think that supernova feedback can actually remove the baryons here, because of course, after all, these objects are very small, so the potential well is not so steep. You can actually remove the gas relatively easily. That mechanism actually gets harder and harder as you go towards more massive galaxies, because the potential gets steeper. At the other end, you cannot eject them via supernova, so the other option is AGN, which is very fashionable. Still, as I said, these things are not proven at all. These are things that we believe might be the options, but it's not clear. There are no models actually showing beyond any reasonable doubt that these things are the main mechanisms. So other things like gravitational heating might be playing a role here. But the bottom line is that there must be several mechanisms playing a role, and the connection between dark matter and the bright matter is a very good way of trying to understand these different issues. So I'm going to just go into the first part of my talk, which is the dark side of it, and I just present this picture to illustrate what I'm going to be working on. The way, of course, of dealing with dark matter is indirectly through the effect that they have on the stuff surrounding it. So one option is to look at the kinematics of stars or gas, and you try to see, for instance, the rotation curves in late-type galaxies and spiral galaxies. You actually see that the motion cannot be explained only by the baryons. In this case, I'm going to be using strong gravitational lensing, and this is a very nice illustration. What happens if you put between this little building here at UCL and ourselves, we put a transparent but massive galaxy, and you see what happens there. The image gets distorted because of gravitational lensing. Basically, the photons have different trajectories. They are distorted by the presence of the gravitational field. And the interesting bit for us is that you have this window mapped into a distorted window out here, and in here you have another image of the same window. And that's an important point, because you have double or quadruple images of systems, and you can use those positions to try to infer the mass. So that's a way, that's your dark matter telescope. That's the way you can determine the masses there. So I'm just going to skip that because I think it's not worth it. But the bottom line, I just wanted to point to this block here, where basically the main issue is that you have a system like this. This is the Einstein cross, and you have a quadruple system. This is, in this case, a bulge, not really a galaxy, what is acting as a lens. But what you do is you use those positions, 1, 2, 3, and 4. You use those positions and the geometry of the lens. So the source, background source is here. These are the images on the position at the position of the lens, and we are here. And you use those positions and time delays to determine the total surface mass density. So again, another crowded plot that I'm going to skip, but I just want to say two things here, that what you do is we take systems like these ones, okay? These are the real things that we are looking into. And what we do is we take the positions, so position 1 and 2 here, position 1, 2, 3, and 4 there. We use those positions and time delays, if they're available, to determine the total mass according to gravitational lensing. So that's one piece of information. At the same time, because we have brilliant imaging from HST, we have, in this case, we're using, well, old we've picked 2 ACS and NICMOS. We have imaging of these guys in different bands, and what we do is we use that light in order to determine a stellar mass content, okay? So we do a bit of a comparison with different models. And that's what I wanted to show here, that you have these two sides. This is work done by Dominic Lyer, a student in Heidelberg who finished his PhD thesis this year. And, but the main issue is this line that I'm plotting here. Just get out of this one. Oops. So the main point that I want to make is this line here. What I'm saying there is that the way you determine the stellar mass and the way you determine the lensing mass is absolutely independent. It's as if I'm doing two different experiments. So there is no systematics there. For instance, you may think, well, why don't you use the central velocity dispersion of the galaxy to add more information about the mass? But then I'm actually biasing because the velocity dispersion can affect the analysis of the stellar population. So we don't want to mix them. We want to make them as independent as possible. And what we find is this. So here we are plotting, basically imagine that we take one of those galaxies and we have already our surface mass distribution in total mass and in stellar mass, and then I have circular apertures, and I keep on increasing the size. So I go from a very small one, labeled here as 0.25, which means 1/4 of the effective radius, the half-light radius, half of that half-light radius, 1 half-light radius, and out to 5 half-light radii for some of the lenses that we can observe. And we plot here the enclosed stellar mass with respect to the enclosed lensing mass. So this line here in all the panels, this line here represents the one-to-one correspondence. And you can see that, of course, all of them are above, which means, of course, there must be more lensing matter than stellar matter. Otherwise, we would be in trouble. And you see that within error bars, basically all of them, except for this object, which is a bit problematic, and I could talk to you about it, but most of them, all of them, basically have this trend. But not only that, as you increase your aperture, they drift away from this line, which means that basically the more you open the thing, the more you measure outside of the central region of the galaxy, you're measuring more dark matter. Basically, there must be more dark matter. There's not enough stellar mass to explain this trend. And this is a very important result because that shows, in the plot that I presented in the beginning, that shows this baryon fraction issue that I mentioned, that in the central region, so for example, for these galaxies, as you move further out, you keep on having a lower and lower baryon fraction. And also, the second trend that may not be so clear here is that trend is more acute when you're dealing with the most massive galaxies. So these ones at the top here drift faster than those ones that happen to be further down. So the main idea is not only you have more dark matter the more you move further out, but in the more massive ones, that trend actually is more significant. Because we have that two-dimensional surface mass distribution in stellar mass and lensing mass, one of the things you can do is go beyond just a simple counting the mass inside. So one of the things is, how is mass being distributed? And the zeroth order approach is, rather than trying to do a fit that I will show you later, what we did here is a very simple thing. Imagine that you take just the whole extent of the galaxy, as far out as you can get it, and you say, well, where do I have 50% of the mass enclosed or 90% of the mass enclosed? And you take the fraction, the ratio of these two. So depending on the difference between the two, that already gives you an idea of, if you want, the slope of the distribution. It's very rough. This is if you want zeroth order approach, but it's very robust. And when you plot that, which is a measure of concentration, you see a very interesting separation. So this and these represent the same objects, but here we are representing the concentration in the stellar mass, so in the baryon content, and here this is the concentration in the dark matter, if you want, in the lensing content, which is dominated by dark matter. And what you see is, first of all, when you're dealing with low mass galaxies, remember I told you low mass galaxies are not so dominated by dark matter. So their baryons are pretty much all there is. In that case, as expected, you see that the concentrations are very similar in both cases. But as you go towards more massive galaxies, more dark matter dominated, you find that the concentration in dark matter goes down, whereas the concentration in the baryons goes up. And this is interesting and, in a way, something to be expected, because in the standard scenario we have, you have the baryon physics driving star formation, which is what is creating this. And this one is driven basically by the assembly of structures. And that is different. For instance, these objects, if they have some sort of evolved process of formation, one of the options, one possible explanation is that these objects, because they are more massive, they might have been formed later on, background density being a bit lower, you end up with lower densities. And this is, for instance, what people get from simulations, embodied simulations. It's not the only possible explanation, of course, but this shows, again, the dichotomy, the two different behavior that you have in the dark matter and in the baryon content. We try to go beyond that. And I don't want to make this one too messy, but we just said, okay, if we try to make a fit, you cannot do an arbitrary fit. You have to basically use some sort of a well-defined function. And so what we did, so again, we have inherent degeneracies here, so we have to take this a bit more carefully. What we did is we were fitting the dark matter with a so-called NFW profile named after Navarro, Frank, and White, a very typical profile that happens to be a very good representation of the general profile of dark matter structures. And then you have the baryons modeled by a Hernquist profile, which is similar, just gets steeper in the outer regions. The reason for a Hernquist for the baryons is that when you project, these are three-dimensional profiles. When you project them in an image, a Hernquist profile gives you something very, very similar to a Vauquelin, to an R⁴ law. So it's a good representation of a galaxy after all. So with that caveat, if we take those functions at face value, we end up getting those sorts of fits. As I said, I won't go much into the details of this because there's lots here. But the bottom line is that out of this parametric fit, one important parameter that we can get out is the concentration that people like dark matter, if you want, cosmologists would use. Because when I do this one here, the one I showed already, the problem with this one is, of course, it depends on the extent of the galaxy. So you try to do some sort of a Petrosian approach if you want to try to get as much of the galaxy as possible. But, of course, that's not always going to work. Whereas this one tries to basically go as far out as possible and define a concentration as a more, if you want, consistent entity. So when we do that, the concentrations that we get out of this fit are those red dots here. So this is concentration with respect to the virial mass of our system. Now, of course, we have an understanding of the halo, so we can even assign a virial mass to these systems. And you find something very interesting. These points here are data coming from X-ray work done by Buot and collaborators. Other points actually would fall also very close there, but this is an interesting paper that we combined. And they're dealing with groups, mainly very massive galaxies groups and clusters. And you can see that our concentration is some sort of extension. It's not, of course, with error bars, which you can see here as these confidence regions here, but still you see that there is an extension of the trend towards galaxy scales. So it's actually quite interesting. So you find that, as I mentioned before, the more massive things are actually less concentrated, the least massive things are more concentrated. These are coming from dark matter simulations. So these are lambda CDM simulations of Neto and the group of Navarro and Frank. And you can see that the trend is the same. As you go towards more massive halos, in this case, you get lower concentrations. But the problem now, have a look at the scales. This is of order 10. So they hit 10 at maximum, whereas 10 is in our case over here. This is a well-known problem. And it's still something that is not well understood. So this is quite important to see. Of course, there can be many problems, mainly because these systems are basically too simple and too easy to define, whereas a real thing as a galaxy would be much more complex. But these things have to be taken into account. And in a way, that could also show that the modeling approach may not be right after all. So we have to be careful. One final thing in this dark sector of my talk has to do with, if you want, the next step. What happens when you have the baryons and the dark matter initially in some sort of homogeneous distribution at a low perturbation with respect to the background? The baryons fall into the center and form the galaxy, and because they contribute so much in the central region, the density, if you want, is so much higher, they actually have some sort of back reaction on the dark matter. So that means they change, they steepen, they should steepen actually the dark matter profile, just because there's more matter inside. So even though baryons don't dominate the overall budget, if you put all of them at the same corner of the room, of course they're going to have an effect. And that's one of the things that people have been trying to do. So the classical approach was of Blumenthal et al. In 1986. The main idea was simple conservation of angular momentum, where you have things like, if you want, in circular orbits falling, you have some sort of shells collapsing into when you're forming your galaxy. And using this conservation of angular momentum, what you can see is, well, this is before and this is after, and it must be the same. So basically, the initial distribution, this is the cumulative mass within a given radius times the radius, so angular momentum. This is initially because they were not separated, they were mixed, equals the later stage where you have the baryon content on the one hand and the dark matter content on the other one. So you have the galaxy and the halo there. And basically you use this to try to infer how much the dark matter has been contracted after the process of baryon collapse. This was reviewed later by a number of papers, but this was one of the really interesting ones by Knieding and collaborators, where basically there was a number of simulations being done trying to prove this approach, which, I mean, this is pretty much back of the envelope, this one up here. But this one was actually trying to back this with proper simulations. And what they found, and this is one figure, is that when you're trying to do this analysis in a very simplistic way, sometimes you basically don't get, you can get differences. So this is one of the options. When you have the standard adiabatic contraction, you see differences between what you see and what you should expect. And you can get improvement, which would be these lines here, when you have a modified adiabatic contraction, which is down here, which is quite simple to define. Basically, you substitute your radius here by an orbit averaged radius. So basically, it's the same, but rather than having its radius at a given position, because you have orbits of different eccentricities, you just make some sort of average. And when you do that, it happens to be working much better. So this is what you see over there, and you actually see a much better agreement. So we try to explore this. You have the classical one, you have this one motivated by simulations, but the problem is, of course, simulations are simulations after all, and you can have very complex mechanisms at play that can change your whole business. So what we're doing is a very simple test where we have the classical one of Blumenthal 86, the Knieding 2004, and what we do is we assume that you have an initial concentration and you have a baryon fraction. You follow their prescriptions, as simple as that, and you end up with a final concentration. And what we do is we compare those final results with the observations that we have. Of course, taking at face value all the different caveats that we have. When you do that, you find that our data points, again, large error bars, I cannot pretend to be able to have high precision things here because they are very complex, but you see that they basically don't fall within the regions that you would expect. This would be the range of concentrations, as you see here in this grayscale. So this is when you're plotting the final concentrations with respect to the baryon fraction. And you see that the trend, so you go from low mass galaxies to high mass galaxies down here, but it just goes this way. It's not as high the concentration as you would get. Neither in Blumenthal, which is huge, nor in Knieding, where the concentrations, as you can see, are lower, so the level of contraction is not so strong, but still is way too high. So we just did a very simple thing. Well, why not change those parameters? After all, it is an ansatz, so we can change the numbers at will. And what happened is that this is what we get for a reasonable fit, roughly. And what happens here, so you see the value of A and W, and again, there's lots of meaning behind those two numbers. But the bottom line is that the process of contraction was not as strong. And the main thing is that you cannot have a very simplistic picture where you have the dark matter being driven by the collapse of the baryons, because when you have things, for instance, like a merger, some stuff falling in, or even some stuff being ejected, that is going to have also a very strong effect on the central profile of the dark matter. And that actually may not only wash out adiabatic contraction, it could even reverse it. So it could, for instance, develop a core rather than having a cusp. And that's why there are, these papers that can explain this. So you can have baryon ejecta, like star formation driving gas away, the classical Deckel and Silk scenario, or dynamical encounters with smaller structures. So these papers dealing with, for example, structures in clusters, or in Cole et al., they have a very nice toy model where you basically drop some stuff in, and they consider that it could go away, and they see that you go from a very cuspy profile to something that has more of a core. So this is important there. Okay, so I'm just going to switch now. So I will have something like 15, 20 minutes, possibly. So I'm going to switch to the other side of the bright side. Sounds more positive, even though it's both are equally interesting. So we're going to go to the bright side of early type galaxies. In this case, the messy bit happens to be the interpretation of the stellar populations. And of course, as you know, it's a big mess, because when you're dealing with resolved stellar populations, when you know them one by one, it's already a mess. It's already very complicated. So when you're dealing with billions of stars, all of them in one go, as one entity called a population, you can imagine that trying to constrain those things is a bit of a challenge. That's what we're trying to do here. And this is a very simplistic scenario where you say, well, you have the data here. maybe some priors because you know something about them already from some other observational evidence. Then you have, your population synthesis models, stellar libraries. You have a very, very strong group here at the IAC working on these things. And then you put them together and you have some sort of estimates of different properties like age, metallicity, dust, etc. So one of the things that we have been doing recently in collaboration with a good number of people here at the IAC was exploring a huge sample of about 40,000 spectra of early type galaxies in Sloan and imaging as well. And we combined spectra and imaging both in the optical and in the infrared. In this part, we only did the spectral side of it. So Ignacio García de la Rosa here, one of the IAC usual suspects, has been actually leading this nice work, where you actually try to see how different the star formation histories are, with respect to the mass of the galaxy. In this case, we take the dynamical mass. So from very massive galaxies to lower mass galaxies, early types, all of them, you see that here most of the stellar populations happen to be very old, older than about 10 gigayears. And here, as you go towards lower masses, basically the histogram gets more and more spread out. So the nice thing about this bit is that we did the analysis in a very good way, free of systematics. And it's interesting to see that the results were rather robust. So this is just dealing with the spectral fitting. But you can also have information about the alpha iron abundance ratios. These are very interesting. For those of you who don't know about this, the main idea is that you have different types of elements that are coming from different types of stars, if you want. So iron comes mainly from things called type 1a supernovae, which are binary systems. So there's a delay because you need to form the binary systems. Those things are actually low mass, so it takes longer for them basically to be in that situation. So that would be, if you want, the source of iron in a very simplistic way. Alpha elements are coming from explosions of single isolated stars that undergo core collapse. So those are very massive, 10 solar masses higher, which means that we're talking about much shorter timescales. So the thing is, when you compare the different ratio in those abundances, that gives you an idea of a clock, in the sense that lower abundance ratios means that you have had enough time for the iron to be incorporated into the stars, which means that your star formation process must have been taking place over a reasonably long period of time. So we're talking more than 2, possibly 2 or 3 gigayears. Whereas when you're here at the high alpha iron, in that case, the star formation process must have been very quick, because no matter what, that iron that was generated by type 1As could not have been incorporated into the stars because star formation was long gone. And that's why we have this. And here we're talking about timescales of order a gigayear. And you see that, interestingly enough, not only these things are actually very old, but their alpha iron is very high, suggesting that the fraction in very old stars happens to be as high as 60 or 70%. Stars older than 10 gigayears. So not only they are very old, but they have very short-lived periods of formation. And this is already something very important, because these guys, as I said, are very massive. So from if you want the dark matter point of view, you need some sort of a complex situation to have them in place. So it's important to put this in context. Another thing that we have been doing recently, a PhD student in Brazil, Marina Trevisan, did this really nice work where she was actually comparing the assembly history of these galaxies. So these are our galaxies here in black, compared to a general population. This is in blue, work done by Pablo Pérez González at Madrid University. And you can actually see here, especially for these guys, so the most massive guys, you can actually see that when you're concentrating on early type galaxies, you have a very, very short-lived process of formation. So you see by that redshift, I mean, this is, again, take this with a grain of salt, but by those redshifts, you already have those populations already formed. Okay, so it's very important. So again, revealing this idea of a very short-lived period of formation. However, the problem there, and Ignacio would quickly say, is that all these observations are based on the central region of the galaxy, where you're actually taking most of your light. The brightest spot is actually there. You have to get a bigger picture. You have to open your aperture. You have to open up and see something else. The problem there is, of course, if you try to do this thing here, we would need a massive survey to do spectroscopically, long slit, try to go far out, or with an IFU, and have 40,000 galaxies observed in a similar way. So the coward's approach is photometry. Don't quote me on that, but we did that because we couldn't do anything else. But the advantage here is that we used the Sloan photometry, as you see, so G minus R, G minus I, G minus Z. But then we also have UKITs, infrared, so Y, J, H, K. So we go all the way to 2.2 microns for the same sample. We have the imaging, and we did a very careful analysis of the color profiles all the way out to about 8 effective radii. And here the complications with things like the PSF actually are quite huge, so we have to be very careful. And you find that consistently, all these profiles show a bluing of the trends. But of course, it's far from trivial. I mean, you see some of these differences depending on whether you're dealing with G minus I or G minus Z or G minus R. So what we have to do is pass all this information through modeling. And the advantage of having infrared on top of optical is that you can have some sort of breaking of the degeneracy between age and metallicity. As you may know, if you use photometry alone, you have huge degeneracies. I mean, even spectroscopy, you have big degeneracies between age and metallicity. And only by carefully selecting some regions that are more dependent on either age or metallicity, you can begin to understand how to separate these two. So we did that with a batch of different models that we had there. So we had the advantage of having Gustavo Brusual and Stéphane Charlot joining us in this project. So they gave us all the models we could dream of. And even so, they're not final yet. So we actually had to rename them. So this is an older version. They're not even called CV13. So who knows when that will come out. But the main idea is that you can see the main results. So these colors, this is color-coded with respect to the mass of the early types. These are stacked. So the whole thing is about, here out of 40,000, we selected 674 very good galaxies there to do the imaging, and we split them according to the stellar mass. So you see we go all the way to higher than 3 10 to the 11. And you see that to the first order, so you see the trend in age and metallicity as a function of radius for model A, B, C, all of the different models, right? You see that regardless of the models, to first order, we have a very strong trend with metallicity. No big deal, we knew that. The central regions are more metal-rich. The outer regions are more metal-poor. No matter which model you use, you find that, and you have that for all the different stellar masses. So from intermediate to high mass, all of them actually have the same trend. Now, the second order thing is age. You can see the age plot, the top portion of this figure, gets messier. You see, depending on the models you choose, you may get one thing or another. So that's why you cannot claim too many things here. But you should agree with me that no matter how you look at this, you get consistently older ages in the outer regions. And it's actually quite an important result. So this is to second order. On top of that, you also see that the red point here in metallicity always falls on top, no matter what. Basically all these, except for maybe some of them, but pretty much all of them you have this. And when you do the numerical analysis, you do confirm this. You find that the metallicity gradient happens to be steeper in the more massive subsample of galaxies. And this is very important information, because if mergers are very important, what mergers are doing is they're actually washing out the gradient. Basically, if you have the standard scenario where you have your gas funneled to the center and then forming stars, maybe in an inside-out scenario, you see that you're going to develop a very nice, very tight correlation between metallicity and radius, so that in the central region, you cannot remove stuff, and you basically build up your metallicity. Outer regions, you remove this, and you get lower metallicity. You have a merger coming in, bang, it hits it, and then it starts actually messing up the picture. So this might be interpreted in the sense that possibly the more massive ETGs may not be so affected after all by mergers. That's actually an important point, yeah. Depending on the models, again, so BCO3 models, you do get that. You see big differences between, for example, this is Brusual and Charlot 03, and this would be the Brusual and Charlot 2007 with Stelib. So that's why I said don't emphasize, I would not emphasize so much on the absolute calibration of the ages. From model to model, you cannot compare, so I wouldn't. No, so that's why, again, as I said, the relative differences are the ones that are robust. The relative differences, not the absolute differences. So, and if you want, the second thing is the other spectral analysis is based on some of these models. It's actually, some of them can go quite low. So no. So I agree with you. As I said, you cannot believe the absolute calibration because it's messy. But the bottom line is, no matter how model you choose, you end up always getting a significant difference. Okay. Another issue is how older are these populations in the outer region with respect to the central region. That's a matter of debate. And nobody working in this field would actually try to claim that they have very small error bars, because it's actually a very difficult task to do. Okay. So, and as I said, if I have to trust, of course, I definitely go more for the spectroscopic approach. But as I mentioned, there you don't have the ability of tracking basically the gradients. You only have central regions there. Okay, so I think I might just skip this one. I just briefly to say this sample happens to be local, so this is the redshift is below 0.1. If you go further out, this is a sample that I worked on some time ago on massive early type galaxies at redshift about over the 0.7 in median, going out to about 1. And you see this is again the color gradient vertical, and you see that for the masses we're dealing with here, which is higher than about 10 to the 10, all these red dots happen to be below the 0 line, which means they have red cores. So again, you have similar types of color gradients, and interpretation is also similarly mainly driven by metallicity. Sorry, here, because if you have a metallicity sequence, so this is the central part of the galaxy, the outer part. So if the color is mainly driven by metallicity, basically this is not going to change as you observe more and more distant galaxies because you're not playing with the age. Whereas if you assume that the central region is redder because you have older populations, you're actually going to invert. You're going to have a very
We have time for a couple of questions.
So Ignacio, in the light of your last result, how much do you need to revise the first conclusions about dark matter content?
So yeah, that's a very good. However, I can say that in the lensing analysis, if you're in the central regions, you may have a point. You may say that within an effective radius, sometimes we obtain that we need something like, I don't know, 50 or 60% of dark matter. That may actually move down, even move down to zero, which is what Michele Capellari has been saying, that it might be even possible to remove the need for dark matter. So that is fine. When you move out to 3, 4, 5 effective radii, there is no way, because the increase in the lensing mass goes way above anything that you could generate with baryons. So yeah, that is actually fairly safe. But in the central regions, you're absolutely
right. Could you please say a bit more about this change in the IMF and the Mach number, and also put into the context of this mass accumulation that you are allowed to have in these networks, in the center of the networks? I mean, so could you say more, a little bit more?
You mean with respect to the IMF?
Yes, because first you said that you're allowed to, I mean, this pseudo-hierarchical thing, you're allowed to accumulate the mass in this central of the networking things, and then you accumulate the mass, and this mass is not going to avoid the star formation, but it's able to keep forming stars for some way. And this,
the cold accretion.
but this also you have to do with the IMF thing that you have at the end, right?
Absolutely.
Okay, and that has to do with the behavior of the gas after a high Mach number. Could you say a bit more about this?
Yeah. So that is still a bit of preliminary work. So I couldn't actually elaborate so much on it. But you're right. It depends enormously on the channels that you have. So we have to be a bit careful, because sometimes when we talk about this process, this very early process of violent star formation, I'm just going to show this one. Sometimes people use so-called exponential models, decade models, and you end up having things like this. So this is just because of the modeling. You end up having that the galaxy must have been formed over a very, very, very short period of time. And now we're talking actually a time scale lower than about 200 million years. So that means you must have a sustained star formation rate of above 1,400 solar masses per year. That is huge. That could actually become a problem, because the energy balance that you have, you may even actually be driving it some sort of, if you want to add into an argument, basically you're driving all the stuff out. You basically are injecting too much energy from feedback. But in this case, you have things that are actually more consistent with recent simulations. We're talking about 100, 200 solar masses per year over a period of 1-2 gigayears. That is not so bad. So that is a process that can be sustained. Of course, this means we're not going to have an equivalent of 82 at redshift 5. We're going to have a monster. But still, the energetics behind this are actually not so crazy. So I mean, that's the essence of it. Going in details gets messy, and you can talk to Carsten Weiner here, who is an expert on IMF. And I was talking to him last week, and it's still very controversial. So Hopkins' argument is very simple, maybe too simplistic. It's nice because it works in the right way, but I would take that with a bit of caution. It's some sort of, if you want, a back-of-the-envelope test that works fine. Carsten's work actually may be suggesting something that could be different. So it's not clear. I think it's still an open question to find this. Even the whole concept of these objects, thing is, we have all these, I don't know, the scuba galaxies, the sub-millimeter, all those objects. So in principle, are those the objects that we're dealing with here? We still don't have a clear argument of saying, look, these are the objects that we're dealing with. These are the physical conditions that appear in our systems. But with regards to the IMF, my usual reply to this is, why not? It has been kept universal and fixed for years. And the main reason is because it's simple and we don't understand it. So let's keep it. So the IMF is bound to be different because it basically goes inherently in the different properties of the star-forming region. So if you have a very severe starburst, or you have something like the Milky Way where you're idly forming stars, you cannot have the similar properties. So the fragmentation is bound to be different, and the spectrum of stars is bound to be different. The mass distribution is bound to be different.
Okay. I have a question concerning the stellar accretion that you mentioned. Is this something that occurs together with the inflow of cosmological gas that is falling into these stars that are formed in these cold flows? And this accretion of stars depends on mass, in the sense that also dwarf galaxies should have them?
Well, there are several issues here because so one is the process of star formation during a cold accretion event. And the other is what you're mentioning is possibly this Osser mechanism. Just to be sure. So are you referring to this one? Where you basically see how stars are being formed in different regions and being incorporated into the galaxy.
Probably I'm talking about something more general.
So, I mean, you see, it gives a level of the complexity and of how little we really understand about the basics of it. Because in terms of cold accretion, it's still an open question. Because it's still, so the bottom line is that you can basically have a huge amount of gas falling into a very small part, into 1/10 less of the virial radius, without being shock hit. So basically you can fuel star formation. After that, simulations basically all bets are off. We really don't know properly how these things evolve. This one is, if you want, better understood. This basically tracks a cosmological simulation where you have your dark matter, your gas, and then you have a very simplistic prescription for star formation. And what you find is all those stars that happen to be in massive galaxies later on were actually formed elsewhere. So this is telling you that process of formation did not take place while the gas was flowing. So gas was not the important bit that accretes, but stars. So that means the stars were already made further out.
So outside galaxies?
Outside those smaller galaxies, of course. So minor mergers means you would have like dwarf galaxies, smaller galaxies that are possibly gas poor and then end up raining into the massive galaxy later on. Keep also in mind that massive galaxies live in overdense regions. So the environment also is going to be different from a normal galaxy. So also that could play a role in the sense that when those galaxies fall in, for instance, they might be, at low redshift, they can be ground pressure stripped. So the gas can actually be removed from the system. So there are complex processes that could play a role. But on top of that, let me tell you, these guys published this very nice results, but